Good morning, everyone. Today we have to discuss about the second unit. That is nothing but feedback amplifiers. So I have to share the screen now. All of you observe. Okay. So here we have to discuss about the feedback amplifiers. First of all, you have to see the course outcomes, course objectives, and what is the syllabus it consists of. After that, we'll go for the Bloom's taxonomy, right, ma? So now we have to discuss about the. So this is our course objectives. What here we have to discuss about the feedback amplifiers. So to familiarize the course objectives are to familiarize the concept of feedback in amplifiers. So for the and as to differentiate between the negative and positive feedback amplifiers. Okay. So here what we have to do. So to familiarize the concept of feedback in amplifiers and to differentiate between what is meant by negative feedback and then what is meant by positive feedback amplifiers, right? So we have to discuss about these are the course objectives for the second unit, that is nothing but feedback amplifiers. Then we'll go for the what about the syllabus of this? Already you have to study about the first unit. The first unit consists of two parts. One is nothing but multi-stage amplifier. Second one is second part is transistor at high frequencies. So already you have to discuss about the classification of amplifiers, distortion in amplifier, different coupling schemes used in amplifier, frequency response. What are the different coupling schemes? Those are RC coupled amplifier. Next one is LC coupled, LC tuned amplifier, transformer coupled amplifier, direct coupled. All these are the coupling schemes used in. How many types of distortions are there? Mainly three types of bit distortion. Already we have to we will discuss all these will be discussed in the first unit. How many types of distortion? Anyone of you tell me? So there are mainly three types of distortion. One is amplitude distortion, frequency distortion, as well as phase distortion. And then already we have to discuss the classification of amplifiers. And then we have to see about the frequency response and analysis of multi-stage amplifier. What we have to discuss here now? So here we have to find out the lower cutoff frequency, upper cutoff frequency, and mid frequency region. For the lower cutoff frequency, we have to find out the lower cutoff frequency. Then we have to find out we have to take the high pass output. For we have to find out the higher cutoff frequency, then we have to take the low pass filter. Anyway, mid band frequency is anyway almost all constant. Next one is we have to go for the cascaded RC coupled amplifiers. So what is meant by cascade amplifier? Cascade amplifier is nothing but two RC coupled are connected together here. The output of the first stage is connected to the input of the second stage. That is nothing but cascaded RC coupled amplifier. So it is also known as cascaded or RC coupled amplifier. Second one is cascade amplifier. Already we have to discuss this. What is the combination of cascade amplifier? Any one of you? So it is nothing but this amplifier consists of CE followed by CB. And then what is meant by Darlington pair amplifier? This is CC followed by CC. Already we have to we'll discuss all these multi-stage amplifiers in the first unit. Next, we'll go for the transistor at low frequency. Already we have to study the multi-stage amplifiers as well as single-stage amplifiers. You have to take the H parameter model. That is nothing but low frequency analysis. This is for the transistor at high frequency. So here we have to go, we are not considering the any capacitance value in the multi-stage. Here at the transistor at high frequency, you have to consider the capacitance also. Here we have to find out the we have to draw the hybrid pi model of the common emitter transistor model, and then it is like a pi. So it is known as hybrid pi model. So it is also known as Giacoletto model. And then we have to find out the F alpha, F beta, and F infinite. F alpha, F beta, and Ft. And then we have to find out the gain bandwidth product. Okay, all these will be discussed in the first unit. Now today we have to discuss about the feedback amplifier that comes under the second unit. What it consists of feedback amplifiers, and then what is the concept of feedback amplifiers, and then classification of what is the concept of feedback and comparing to the amplifier, what is the concept of feedback, and then classification of feedback amplifiers, and then general characteristics of negative feedback. Classification of feedback amplifiers are nothing but how many types of feedback amplifiers are there. The negative feedback amplifier, we have to discuss this also. And then what are the general characteristics of negative feedback amplifiers? So we have to discuss about the what are the general characteristics. So then only we have to know the condition of the that feedback amplifier, particular feedback amplifier. And then what is the effect of feedback on amplifier characters? This also we have to derive by using the equation. And then we have to find out the voltage series, voltage shunt, current series, and current feedback configuration. And then we have to find out the simple problems. This is comes under the unit 2. Right, ma? Any doubts in the unit 2? This is our syllabus, right? Then we'll go for the what are the course objectives. So after completion of this unit, all will be understand the what are the concepts used in the negative feedback and how to improve the stability of amplifiers in the negative feedback amplifier. And one more thing is how the bandwidth will be increases by using the negative feedback amplifiers. Okay, ma. These are the course objective after studying the second unit. And then this is the Bloom's taxonomy we have to use. First level is remembering, and the second level is understanding. Third level is applying, analyzing, evaluating, and then creating. So we are having total 6 levels are there. What is the first level, ma'am? So this first level indicates the learner can be remember the what about the information about any of the amplifiers, circuit, amplifiers, and then they have to understand and explain the ideas as well the concepts. Here we have to, for the level 1, it consists of the these types of questions will be available. So that is define, duplicate, list, memorize. So what are the define what is meant by define what is meant by feedback amplifier. List the various types of feedback amplifiers. Like this, they are asking the question in the university exam. Recall, repeat, as well as state. This is comes under the level 1. And then level 2 it is understanding. Whatever you have to study in the first concept, that will be understanding by yourself. So the learner can be explain the ideas as well as concepts. So what are the questions they are? Classify, describe, discuss, explain, identify, locate, recognize, report, select, translate, and so these are comes under the under level 2. And then we have to go for the third level, that is nothing but applying whatever you have to study in the definitions or the concepts, and then you have to understand, then these will be applied in the application part. So the learner can use this information, and then we have to create the apply in the those circuits. Suppose in our ECA subject, we have suppose we have to take any of the circuit, and then we have to discuss about this thing. After that, we have to understanding this. Then that will be applied to the any of the amplifier, and then you have to analysis that one, and then you have to evaluate. So you have to evaluate by using this fifth level, and then you have to create any of the new circuit diagram, and then where it can be used. These will be sixth level. So for that analyzing, the learner can distinguish between different parts of this, and then we have to how they are like this: appraise, compare, contrast, criticalize, differentiate, discriminate, distinguish, examine, experiment, question, test, like this. This is fourth level. And then evaluating. So can the learner can justify a stand or decision. So here appraise, argue, defend, judge, select, support, value, evaluate, like this. So and then level 6. So whatever you have to study up to here, these will be you have to create any of the new circuits. So these will be assembled. So whatever basic components are there, that those will be assembled here. Okay, by the, and then you have to construct the any of the, and then design any of the new circuit, develop or formulate, right? Like this, all these are concerned at the Bloom's taxonomy, right, ma? So all these 6 levels are, this is low level, this is high level. So all these will be defined in the Bloom's taxonomy. This is our revised Bloom's taxonomy levels, right? Then we'll go further. Today's learning objectives are, the student will be able to discuss the introduction of negative feedback amplifiers, what is meant by feedback amplifiers, and then what are the components, what are the blocks used in the negative feedback. This will be concerned at the first learning objective. And then classify the basic amplifier used in the feedback amplifier. Classify the basic amplifier used in the feedback amplifiers. Okay, these are the learning objectives today we have to discuss, right now. So here, what are the classification of amplifiers? So first of all, you have to go for the discuss the introduction of negative feedback amplifiers. Here we'll go for the introduction of negative feedback amplifiers. Then we'll go for the classification of basic amplifiers. All of you know this. What is meant by amplifier? All of you tell me about the amplifier definition. Any one of you? Amplifier is nothing but it will be strengthen the input signal, and then we have to get the output signal at more strengthened signal we have to get. It will increases the strength of the signal. What is meant by strength of the signal here? The strength of the signal is nothing but, here we have to define that the strength of the signal is nothing but, and so the amplitude must be increases, but not with the frequency, right? No, but not with the frequency. That's nothing but amplifier. Here we'll go for the negative feedback amplifier. What is meant by negative feedback amplifier? Negative feedback amplifier is nothing but whatever the source signal is there, that will be subtracted from the feedback signal. Then you have to get the negative feedback, right now. Whatever the source signal, that will be subtracted from the feedback signal, then you get the negative feedback, right? So here we have to discuss about the what are the basic, classify the basic amplifiers used in the feedback amplifiers. So here we have to discuss the classification of amplifiers. So now we have to discuss about the types of negative feedback. So we are discussing in the later topics, right? Next, we'll go for the classification of amplifiers. Amplifiers can be broadly classified as 4 categories. One is nothing but voltage amplifier. Second one is current amplifier. Third one is transconductance amplifier. Fourth one is trans resistance amplifier. Now you tell me that what is meant by voltage amplifier. Voltage amplifier is nothing but both the input side and output side, both are the voltage sources. Okay, ma'am, both sides are, we have to use the voltage sources. And then we'll go for the current amplifier. Current amplifier is nothing but the input is the current source, output is also the current source. And then transconductance amplifier, here the input is the voltage source and the output is the current source here. And then we'll go for the trans resistance amplifier. Trans resistance amplifier is nothing but output is voltage and the input is current. So all these are classified depending on all these amplifiers can be used in the feedback amplifiers, right, ma? One is voltage amplifier. Voltage amplifier is nothing but both are input side as well as output side. We have to use the voltage amplifier. And then we'll go for the current amplifier. Input side we have to use the current amplifier, current source, and the output side is also current source. And then we'll go for the transconductance amplifier. Transconductance amplifier is nothing but output is current and the input source is the voltage source. What is meant by trans resistance amplifier? The output is the voltage source, input is the current source. So these are the classifications of the amplifiers. These amplifiers can be used in the feedback amplifiers. We'll discuss in the later classes. Next, here we have to go for the voltage amplifier. Already we have to discuss that Input is voltage source, voltage amplifier is nothing but voltage source, and then output is also the voltage source. AB into VA represent, this is one of the voltage source. This is also voltage source. This voltage source is in series with resistance at the input side, and the output side is also VS is AB into VI is in series with R naught. Here also VS is in series with RL. So both are connected in series. Voltage source is connected in the source resistance. Voltage source is connected to the resistance in series. That is nothing but Thevenin equivalent model. So here we have to use the both are Thevenin equivalent model. What is Ri here? Ri is the input resistance. Rs is the source resistance. Vs is the source voltage. AV into A is the voltage that will be in series with resistance R naught. It is also the output resistance. What about RL? RL is nothing but load resistance. This is you have to take the output voltage across the load resistance. That is V naught. So input is voltage and the output is also voltage. So it is nothing but it is a two-port network. It represents a voltage. Both are voltage sources, right, ma? Any doubts in this? So here we have to see the conditions in the next today's class only. Okay, we have to observe the how we have to draw the circuit diagram in the approximate model. Okay, my voltage source is in series with resistance, voltage source is in series with resistance. That is nothing but both are Thevenin equivalent models, right? Now both are Thevenin equivalent models. Okay, what is output, ma? Output is V naught. Input is either VI or Vs. So AV is equal to V naught by Vs. V naught by AV is equal to V naught by Vs. That is voltage gain of the amplifier is equal to output voltage by input voltage or the source voltage. It is nothing but voltage amplifier. Then we'll go for the current amplifier. Any doubts here? Any doubt in the voltage amplifier? Next, we'll go for the current amplifier. Here for the current amplifier, both the sources are current sources. All of you observe here, man. Is the current source and I into IA represents the current source. Current source is in parallel with resistance. Here also current source is in parallel with resistance. That is nothing but both are Norton equivalent model. Both are Norton equivalent model. So here we have to represent my input and output side. We have to use the Norton equivalent model. Okay, ma. So both are current source is in parallel with the resistance. Then this equivalent model is nothing but all the resistances and components, all the sources are replaced by one of the source, that is nothing but current source in parallel with resistance. Here the output is also current source in parallel with the resistance. So both we have to use the Norton equivalent model. Okay, the output is current and the input is also current. So it is depending on the AI is equal to I naught by IA. I naught by, it does not depending on the any RS or RL load resistance. So it does not, the current gain does not depending on the either load resistance or the source resistance, right now. So this is about the current amplifier. Then we'll go for the transconductance amplifier. So transconductance amplifier is nothing but already we have to discuss. So the output is the current source. Current source is nothing but is it in series or parallel, ma? So this will be connected in parallel. So the current source is in parallel with the resistor. So here we have to use the Norton equivalent model, and then input is the voltage source in series with resistance. That is nothing but Thevenin equivalent model. This is Thevenin, input side is Thevenin equivalent model and the output side is Norton equivalent model. What is the transconductance formula? That is nothing but GM. GM is equal to I naught by VI. GM is equal to I naught by VI. So it is independent of the, it is proportional to the either the input voltage is directly proportional to the I naught by VI. GM is equal to I naught by, what are the units for GM? That is conductance. Conductance units are moles, right? This is about the transconductance amplifier. Then we'll go for the trans resistance amplifier. Trans resistance amplifier is nothing but output is voltage source and the input is current source. The output voltage, that is Rm into Ii, that represents V. And that is voltage source is in series with the resistance R0. That is nothing but voltage source is in series with the resistance R0. That is nothing but Thevenin equivalent model. Output side is Thevenin equivalent model, and the input side is 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 in parallel with Rs. That is nothing but Norton equivalent model. For this, the output voltage V0 is proportional to the Is. So it is independent of Rs and RL. For the ideal amplifier, for ideal trans resistance amplifier, Ri equal to 0 and R0 equal to 0. Right, ma? This is about the trans resistance amplifier. Then we have to discuss about the each and every amplifier, right? Then we have to discuss about the each and every amplifier. Then we have to find out the input resistance as well as output resistance. We have to find out the input resistance as well as output resistance. Okay. So all of you note down the circuit diagram for the voltage amplifier. Then we have to discuss the input amplifier as well as output amplifier, right now. So we have to discuss about the voltage amplifier. All of you note down this. This is about the voltage amplifier. Voltage amplifier. All of you draw the circuit diagram for the voltage amplifier. Then we have to find out the input resistance as well as output resistance. Now tell me that what is the input and output resistance? Input is voltage source and the output is also voltage source. Voltage source is nothing but input side. We have to use the Thevenin equivalent model. Voltage source is Thevenin equivalent model, and the output side is also we have to use the Norton Thevenin equivalent model. Thevenin equivalent model is nothing but both we have to use voltage sources. Both sides we have to use the voltage sources. So both sides we have to use the Thevenin equivalent model. That is nothing but both are voltage sources. Right now, first one is input side is voltage source, and then the output is also voltage source. Okay, then I'll draw the circuit diagram. All of you note down the circuit diagram. So what is the input voltage source? Any one of you tell me, ma? That is Vs. That is Vs. Input voltage source is Vs. That is in series with Vs is in series with Rs. All of you note down the circuit diagram. Vs is in series with Rs. And then you have to represent Vs is in series with Rs, and then we have to connect the one of the resistance, that is nothing but so Vs is in series with, all of you represent the notations. Vs is in series with Rs, source resistance, and then that is Ri. Right now, that is input resistance is Ri, and then you have to take the voltage drop across the resistance, that is nothing but Vi. So Vs represents the source voltage. This is Vs, right now. This is Vs, this is Vi, and then this is about the input. Input is which type of equivalent model? That is nothing but Thevenin equivalent model, right now. Input you have to use the Thevenin equivalent model, and then output side is also Thevenin equivalent model. That means you have to draw the output side also. Output side is nothing but AV into, and the voltage source is AV into VI. That represents the, that is in series with, R naught, and then how to connect the load resistance, that is RL. Right. So this represents R load resistance, and then this resistance represents R naught, and this voltage source is AV into VI. This voltage source is, that is plus minus AV into VI. Okay, ma'am. So this is about the voltage amplifiers. So input is connected to the, that input is connected to the voltage source. Vs is in series with Rs, and then we have to represent the voltage Ri. So what is the voltage drop across the Ri? That is equal to Vi. This is AV into, this is voltage source in series with the resistance or not, right? Now in series with the resistance or not, and then we have to connect the output resistance as RL. This is about the voltage amplifier. Here we have to see the two conditions. One is Ri is far greater than, Ri is far greater than. Note down the two conditions. I'll have to note down the two conditions. One is Ri is, note down the first condition. Ri is input resistance, that is far greater than Rs. Ri is far greater than Rs. What will happen, ma? Here you have to give the condition as, if Ri is far greater than Rs, what will happen? If Ri is far greater than Rs, nothing but Ri value is more when comparing to the Rs value. That's why you have to neglect the source resistance, right, ma? So that's why you have to neglect the source resistance. So what about the, what is the value of Vi? Vi is approximately equal to the, Vs, right, ma? Vi is approximately equal to the Vs. For this case, Vi is approximately equal to the Vs. This is the first condition. Now, going for the second one, second condition is, R naught is far less than RL. So here RL value is more, R naught value is less. Now tell me that AV into EI. Now tell me that AV into, what about the voltage drop across this load resistance RL? That is nothing but R naught is far less than RL, then V naught is equal to AV. V naught is, that represents V naught is equal to AV into, V naught is equal to AV into VI. What is VI? For the input condition, all of you observe here, VI is approximately equal to the AV into Vs, right now? AV into Vs. So here we have to represent the output voltage gain. What about the output voltage gain, ma? V naught is approximately equal to the, V naught is approximately equal to the AV into Vs. Now tell me that what is the voltage drop, voltage gain across this? That is nothing but V naught by Vi, or it is approximately equal to the, it is approximately equal to the, it is approximately equal to the V naught by Vs. Okay, now this is about the voltage amplifier, and then we'll go for the, what are the ideal values. So these ideal values are, ideal values of the voltage amplifier are, if Ri is approximately equal to the infinity, and R naught is approximately equal to the 0. Why? Because why you have to tell these two conditions, ma? Tell me, any one of you, why you have to take the two conditions. One The first condition is we have to take the ideal values Ri and R naught are infinity and R naught equal to 0. These are the two conditions you have to define for the voltage amplifier, right? Any doubts in this? This is about the voltage amplifier. For the voltage amplifier, both are the voltage and voltage sources. Input side is voltage source. All of observe here. Input side is voltage source and the output side is also voltage source. Then voltage source is in series with the resistance. That is nothing but voltage source is in series with the resistance, that is Rs here or not. So for the ideal values, you have to take the two conditions. The first condition should be Ri is far far greater than Rs. The second condition is if R naught is far far less than RL. Here RL value is anyway high. Here R naught value is less. So we have to take the ideal values is equal to R naught is equal to infinity and R naught Ra is equal to infinity and R naught is equal to 0. Here we have to represent the both. We have to use the Thevenin equivalent model. Thevenin equivalent models are both are we have to use input side is a voltage source and the output side is also voltage source. All of you observe in the circuit diagram. This is about the voltage amplifier. Any doubts in this in the voltage amplifier? Then we'll go for the current amplifier. Then we'll go for the current amplifier. Then we'll go for the current amplifier. What is meant by current amplifier? Both the sources are current sources. Input side is current source and the output side is also current source. Now represent input is have to use current source and the output side is also we have to use the current source. Right now both are current sources. Current sources means which type of equivalent model you have to use. Here you have to use the Norton equivalent model. Norton equivalent model. Here also you have to represent the Norton equivalent model. Norton equivalent model. That is nothing but both the sources are current sources. That means both the sides you have to use the current equivalent model. Both the sides you have to use the current equivalent model. Right now, both the types you have to use the Norton equivalent model. Here you have to represent the IA. All of you note on the circuit diagram. IA is in parallel with RS right now. So all of note on the circuit diagram. IA is in parallel with RI and then it is source resistance and then it is we have to connect like this for the all of note on the circuit diagram. What is the input source that represents IA? That is nothing but input source is IA. IA is in parallel with RS. IA is in parallel with RS. That is in parallel with RI. So this is input side equivalent diagram right now. This is input side equivalent diagram. And then we have to draw the output equivalent circuit. So here IA is in parallel with RS and then it is in parallel with RI. And then we have to draw we have to take the one of the output diagram that represents that is nothing but AI into IA. This is also current source right now. So AI into IA. AI into IA that is in parallel with or not. And then that will be in parallel with RL. that is in parallel with R naught. Or AI into IA, that will be in parallel with this is R naught, and then this is RL. What is RL? R naught is the output resistance. RL is the load resistance. Now tell me that what is IA? What is the current source? Here we have to take the two conditions here also. So first condition is, not on the first condition, for the first condition, Ri is far less than, not on the first condition, that is Ri is far less than Rs. First condition. Not on the second condition, R naught is far greater than RL. Not on the two conditions. So what will happen if Ri is far less than Rs? So here we have to represent that if Ri is far less than Rs, then we have to take the condition as Ia is, what is the current, what is the voltage current flowing through the resistance Rs? That is nothing but the current flowing, that is Is. So Ia, if Ri is far greater than, far less than Rs, then Ia is approximately equal to the Is approximately equal to the Is. Ia is approximately equal to the Is. Then we have to find out that the second condition is if R naught is far greater than R naught is far greater than RL. Then we have to know the condition of AI into IA is equal to AI into IA. AI into IA. IA is equal to I naught. I naught is equal to, what is the I naught now? The current flowing through the resistance R naught, that is equal to I naught right now. So this is I naught. So I naught is equal to AI into I naught, right? This is also the current source. This is the current source. And then we have to find out if IA is equal to approximately equal to the IS, what is I naught now? So this I naught is it is approximately equal to the AI multiplied with IS. So now tell me that what is AI? The current gain of the amplifier is approximately equal to the I naught by Is, or I naught by Is. This is the current gain of the amplifier, right now. This is the current gain of the amplifier. Then we'll go for the current gain of the amplifier represents output current by the current gain of the amplifier represents output current by input current. Output current by input current that represents the I naught by Is. Here we have to represent the value. What are the ideal values of current amplifier? Note on the ideal values. Those ideal values are, all of note on this. Ri is far less than Rs. So that means what is Ri value is very less. So that means Ri is equal to approximately equal to the 0, and R naught is approximately equal to the infinity. So we have to represent that this is about the current amplifier. Then we will go for the ideal values. Ri equal to 0 and R naught is equal to infinity. So these are the ideal values of the current amplifier. Any doubts in the current amplifier, ma? So current amplifier means both sides we have to use the current sources. This is current source. This is also the current source. This is Rs. Rs is in series in parallel with Ia. Here AI into Ia is in parallel with R naught. Then we have to represent the values of Ri and R naught. Ri value is equal to Ri is far less than Rs. R naught is far greater than RL. Then we have to find out the two conditions. Ideal values are Ri is equal to 0 and R naught is equal to infinity. Then we'll go for the trans conductance amplifier as well as trans resistance amplifier. Okay, ma. Next one is transconductance amplifier. Transconductance amplifier. Transconductance amplifier. So here we have to define that what is the input and output side. Conductance is nothing but I by V. All of you know this. Conductance is nothing but I by V. Input is current. Current source. And the output is current source. Nothing but Norton equivalent mode. Norton equivalent mode. And the output is voltage source. Voltage source, that is nothing but Thevenin equivalent model. So one is Thevenin equivalent model, second one is Norton equivalent model. Here we have to represent the transconductance amplifier. So now I have to draw the circuit diagram for the transconductance amplifier. I'll have to draw the circuit diagram. Then we have to see the conditions. Right now, I'll have to draw the circuit diagram here. And now tell me that what is the input? Current source. Current source is nothing but Norton equivalent model, that is transconductance amplifier. Transconductance amplifier is nothing but the input. Here you have to represent this transconductance amplifier. Transconductance amplifier. Transconductance amplifier. Here we have to represent the input and output conditions. Anyone of you tell me now, what about the input? Input is nothing but conductance is nothing but input. Input is voltage. And the output is voltage means Thevenin equivalent model. Input is voltage means Thevenin equivalent model. And the output is current. And the output is current means it is Norton equivalent model. And the output is current, that is nothing but Norton equivalent model. Here I have to draw the circuit diagram for the transconductance amplifier. What is the input side? Input side is voltage, that is nothing but input side is voltage is nothing but voltage source is in series with voltage source Vs. Okay, Vs is in series with Rs. And then you have to connect the resistance Ri like this. This is the Thevenin equivalent model. What is this resistance? Anyone of you tell me now? This is nothing but resistance Ri. This is about the Thevenin equivalent model. And then we are going for the Norton equivalent model. What is meant by Norton equivalent model? That is current source. The current source is in parallel with resistance. What is the current source now here? The current source is Gm into Vi. Gm into Vi. That represents the current sources in parallel with resistance or not. And then we have to represent one more thing is one more resistance, that is nothing but or not RL. So this represents RL. Okay, this represents R naught. This is R naught. This is R. So here I have to represent this value as this is R naught. Once again, this is R naught. This is RL. So what is this now? Current source. Gm into Va represents the current source. Okay, ma'am. This is the current source in parallel with resistance. Voltage source in series with the resistance. Here we have to represent the Thevenin equivalent model, input side is Thevenin equivalent model and the output side is Norton equivalent model. Then I have to write the two of the conditions. Those are the two of the conditions. Those are first condition is input is Thevenin equivalent model. I like note down the first condition. This first condition represents Ri is far greater than Rs. Ri is far greater than Rs. Ri is far greater than Rs. What is the Vi now? Vi is approximately equal to the Vi. What is Vi? The voltage drop across the resistance. Ri is nothing but Vi. So Vi is approximately equal to the Vs. What is the first condition? Ri is far greater than Rs. Then VA is approximately equal to the Vs. Okay, now this is the first condition. The second condition is R naught is far greater than R naught is far greater than RL. Okay, now R naught is far greater than RL. Now tell me the condition of R. If R naught is far greater than RL, so we have to represent this R naught value is very high when comparing to the load resistance. Okay, ma. When comparing to the load resistance, that is equal to what is the current flowing through the resistance, ma? That is nothing but I naught. So IL is equal to IL or I naught. IL is equal to GM into IL is equal to GM into VI. So VI is approximately equal to the GM into Vs, that is IL. Okay, IL or I naught. So now tell me what is GM? The trans conductance is equal to IL by Vs. So what are the units for the conductance? Ma? These are ohms. This is about the trans conductance value. Okay, ma? This is about the trans conductance value. Vm is equal to V naught by Vs. That will be. Now tell me that what are the ideal values? Ma? Ideal values. Ideal values are Ri is approximately equal to infinity far greater than, and R naught is far, that is approximately equal to the infinity. These are the this is nothing but trans conductance amplifier. Any doubts in the trans conductance amplifier? Then we'll go for the trans resistance amplifier. Trans resistance amplifier. Trans resistance amplifier. Here we will go for the trans resistance amplifier is nothing but the input and outputs are input is current source and the output is voltage source. So current source is nothing but here I have to represent this value. Current source is nothing but we have to use a Norton equivalent model. Here we have to represent Thevenin equivalent model. Here I have to represent the Thevenin equivalent model. Now tell me that I have to draw the equivalent diagram for the trans resistance amplifier. So here I have to represent the current source, that is nothing but II. Current source is II. II is in parallel with Rs. And then I have to represent one more resistance, that is Ri. This is about the input side equivalent diagram. And then we'll go for the Norton output is Thevenin equivalent model, that is nothing but voltage source. That is nothing but Rm into IA. Rm into IA. That represents the current source is in series with resistance R naught, and then it is connected to the load resistance RL. And then this is right now. So here I have to represent this is R naught, RL, Rm. Now tell me the conditions of Ri is far less than Rs. And the second condition is R naught is far less than RL. So here I have to write the condition. If Ri is far less than Rs, then what about IA? IA is approximately equal to the IS. IA is approximately equal to the IS. And if R naught is far less than RL, then V naught is equal to Rm into IA. Rm into IA. Here IA is approximately equal to the Rm into IA. IA is approximately equal to the Rm into Is. Right now. Now tell me that what is Rm? Rm is equal to V naught by Rm is equal to V naught by V naught by Is. Right now. V naught by Is. So here this value, what are the units for V by I? Those are nothing but ohms. Now tell me the what are the ideal values. So the ideal values are, now note down the ideal values. Ideal values of the current trans resistance amplifier, that is equal to Ri is approximately 0 and R naught is approximately 0. So this is about the trans resistance amplifier. Today we have to discuss about the classify the basic amplifiers. Those are voltage amplifier, current amplifier, trans resistance amplifier, as well as trans conductance amplifier. Here we have to define the either ideal values as well as the input and output resistances of voltage gain, current gain, trans resistance as well as trans conductance. What are the units for the? Anyone of you tell me what are the units for the voltage gain? What are the units for the voltage gain? The voltage gain that represents V naught is equal to voltage gain represents voltage gain. Voltage gain is equal to V naught by Vi. And then we have to represent the current gain. Current gain of the amplifier is represented as you have to represent in terms of AV. AV is nothing but voltage gain. Voltage gain is equal to V naught by VI. What are the units for the voltage gain? No units. Why? Because input is voltage, output is also voltage. Then you have to represent the current gain. AI is equal to, summarize this one, that is equal to I naught by II. I naught by II. This is about the current gain. Next, we have to find out the input and output resistance, trans resistance as well as trans conductance. So here I have to represent this. One is GM. GM is equal to trans conductance of the amplifier. GM is equal to I naught by VI. That is trans conductance amplifier. Then you have to find out the RN, trans resistance of the amplifier. That is equal to V naught by IA. These are the values of the all the current gain for the current gains for the voltage amplifier, current amplifier, trans resistance amplifier, as well as trans conductance amplifier right now. So these are the voltage gains, current gain. Any doubts in the all the types of basic amplifiers? Next, what is meant by feedback amplifier? Now here we have to discuss that basically there are two types of blocks are there. One is nothing but amplifier block. Second one is nothing but feedback. The output of some part of the output is fed back to the input. That is nothing but the feedback amplifier. Here we have to discuss about the feedback basic amplifier. All these are the basic. These will be connected to the feedback network. What is the feedback network? Feedback network consists of only the passive element. Passive elements are nothing but either RLC component. RLC is nothing but resistor, inductor as well as capacitances. So after tomorrow's class, we have to discuss about the generalized block diagram of negative feedback amplifier, and then we have to discuss the generalized block diagram, and then what are the feedbacks used in the networks. Okay. Today I have to stop here, and then tomorrow we will be continued in the next class.